Well, let's take a few minutes to discuss reduction of alkynes. Remember from the addition to alkenes chapter that an alkene reacts with H2 in the presence of a catalyst, typically palladium or platinum or nickel metal, and we reduce the alkene to the alkane. So we add H2 across the alkene, H on both sides, we end up with the alkane. It's a very expensive way to produce simple alkanes like butane, as I've shown here, but if we have a more complex molecule, we can certainly use this to basically reduce or eliminate our alkene. Well, the same thing will happen with an alkyne. We can use H2. The first step adds one equivalent of H2 across the alkene, across the alkyne, and typically we can't stop the reaction here. It is very hard to isolate the alkene from the reaction mixture, and typically we do this in a sealed vessel that holds a high pressure of hydrogen, so there's plenty of hydrogen to do anything we need to do, and the end result is simply that we get the alkane as the product. So you can't stop it here. Again, we get syn addition of the H2. So if there is the opportunity for stereochemistry, we might do that. Of course, it doesn't matter where the alkyne was if we're making the alkane. So, of course, scientists were like, well, what if we wanted to reduce only halfway? What if we wanted to produce the alkene and stay there and somehow prevent this step from occurring? What if we could do that? So they started to explore different mixtures of palladium or platinum along with some other inorganic compounds that would poison the catalyst to prevent that second step, the step I crossed off in red. So they found that using a poisoned catalyst, the one in our textbook is called Lindlar's catalyst. Sometimes you just write poisoned catalyst. Sometimes you might write barium sulfate or other inorganic compounds. We can stop the reaction and obtain the alkene. So no alkane is produced. And of course we get syn addition here as well. So I'll make it clear it's Lindlar's catalyst. We could think about it from an energy diagram perspective. Here might be the alkyne. Might reduce that to the alkene. Reduce that to the alkane. Let me try to draw some. And if we're going to catalyze only the first step, our catalyst needs to change the activation energy of just the first step. And then it would have essentially the same as the activation energy of the second step. And that would be what our Lindlar's catalyst does. It does not catalyze the second step, allowing us to isolate the alkene. So here we have a way to make alkenes, and this way we do get what's called the Z version of the alkene, of course. So let's make a note of that, because on the next slide I'm going to show you how to make the E version. So this takes alkynes, turns them into Z alkenes. There is, of course, another method to partially reduce alkynes, and that allows us to produce the the E version. There's the E version, and this is done with sodium metal in liquid ammonia. So let me make a little L here to show that that's liquid ammonia. So it's very cold, and you get a clear, cold liquid. You can dissolve sodium metal in there, and what that does is allow the electron from the sodium. We know that sodium has one valence electron. That electron gets freed up. It floats around, and it reacts with the alkyne. And we're going to look at the mechanism as to why that occurs to help us understand why we get E stereochemistry here. We're going to use single-headed arrows, single-barbed arrows, I should say, to show the movement of single electron. So I'm going to take the pi bond here, I'm going to split it in half. One of the electrons goes to the right, the other electron goes to the left, and the single electron on the sodium will also come into play, and it will produce a lone pair on the right side. So let me draw the product of that. So now I have an alkene. I've got a single electron on one side of the alkene. I've got a lone pair on the right side. That would give us a negative charge. I can balance that charge with the sodium plus that I just created. And I'm also in the presence of ammonia, and that's going to be my proton source. So I should draw the ammonia with all the hydrogens showing. I'm going to use the negative charge here to grab a hydrogen. I'm going to draw that hydrogen just so we can keep track of it. I still have a radical on the left side of the alkene. I can use another sodium atom to put a single electron with that radical, making another lone pair and a negative charge. That negative charge can react with another molecule of ammonia, and that produces my E alkene. So you'll notice I drew the intermediate right here so that the lone pair was as far apart as possible from the single electron. These are trans to each other across the alkene. They are far apart. And that's because these are both areas of high electron density, and it would be higher in energy. It would be destabilizing to have them next to each other. So let me draw that option in red right here. So this is the other option that we could have drawn in that first red box. And that would be destabilizing to have the single electron and the lone pair cis to each other, right here, right next to each other. Here they are farther apart. It's more stabilizing. So let me cross off this option so we know that that does not form. And our mechanism then shows this is where we get the E stereochemistry from. We're going to put a hydrogen on this position where the lone pair is. We're going to put another lone pair where the single electron was, and then we're going to put a hydrogen there. And you see that we get our hydrogens added in an E fashion. So now we have the means of creating a Z alkene out of an alkyne or an E alkene out of an alkyne, depending on what we choose. Let's look at a few practice problems. So here we want to fill in the reagents to produce these products. And we'll notice here that we have a 6-carbon alkyne. The first product is the E alkene. And as we just learned, sodium in ammonia. And really all you need to write down is Na over NH3. That is the correct recipe for the E alkene. If we want to make the Z alkene, we just need H2 Lindlar's catalyst. So you can write Lindlar's, you can write Lindlar's catalyst, you can write poisoned catalyst, any of those should be acceptable. And lastly, we make just hexane from our alkyne. That's just H2 and your favorite catalyst. In that case, it's palladium. If we let that go as far as it can, we add 2 equivalents of H2, hydrogenating both of these pi bonds to get us to the alkane. So now there's several different ways that we've learned to reduce alkynes depending on what your desired product is. And of course, once we've made an alkyne, we could reduce it partway to the E or the Z alkene, and then we can use the chemistry that we learned in the Additions to Alkenes chapter to do further reactions on these alkenes. Now we can stretch our pathway of reactions even further. We can do some alkyne chemistry, then we can follow that up with some alkene chemistry and have 2 or 3 or 4 steps all in a row to do a short synthetic problem.